Can I ask you?
We're gonna start.
Oh, start.
All right. So why don't everyone take a few minutes, and we've got. Oh, that's a clicker question. Sorry about that. There we go. This is a sample recursive function on a natural number. And see if you can trace through calling this function with the input 7. So take a few minutes and do that. All right, so you've all had a couple minutes to think of this problem. Looking at this problem, there are a few little tricks, which is why I thought it would be interesting to do. So let's start then. So what's our first step to tracing this one? Well, what we've got to do is we look at this and we see that we're applying a function to a value. So we're going to substitute the argument's value into the body of the function. Now I'm going to use ... because I want to save some space, but I'm not skipping any steps here. So we've substituted 7 in for n everywhere in the body of our function, and now we are going to look at this expression and we're going to look at the first question. And the first question isn't completely evaluated. Yeah?
So if we do something internal, we put ... to save space, that would be accepted?
If you're doing it to save space because of a long line, I'm okay with it. But it's really important that you don't, whatever current expression you are working with, you write that all in down. Otherwise, it will be very confusing. You can't use the ... to skip a step. I'm just using it to save some space here because it's long-winded. Yeah?
If we're going to write the entire thing, including this part, we also set the sum on to admin part.
Yes. Yeah. So just to give you an idea, and you should, for the record, always do the first step completely out. I was trying to get away with that because I didn't want to type it, but we'll do it anyways. So the else part would go, what do I got here? I'm doing plus 7 sum of sub 1, 7, some number of closing brackets. I'm not going to bounce. All right. So our next step, we can't evaluate this expression because both of its arguments are not values. One of them is a constant. And so in the next step, we're going to substitute in the 5 for the x. But note that we don't substitute the 5 in for the x everywhere. When you have a constant, you're only going to do the substitution at the point where you try to actually evaluate that function. So when you actually need to. I don't need to evaluate this x here because I don't even know yet if this question evaluates to true. And there's a big difference, by the way, between constants and arguments. For arguments, you substitute them all at the same time. But for constants, only when you have to. All right, now I'm going to use the ... that there because I don't want to write it all. All right, now 7 is obviously not equal to 5. So that's going to evaluate to false. And then we have our else statement there. Now, when the question evaluates to false, we just drop it. So we just drop it out of there. And we're left with whatever follows it, which in this case is going to be the else. Like so. Now, else always evaluates to true. So, when something evaluates to true, we just replace it with the body. Okay. Well, that's a value, but this isn't. So, we're going to evaluate subtracting 1 from 7. And now we make the recursive call. All right, so we need some more space here. Let's do this one. So we get plus 7 like so. Now we've got to fill in this x. Five and 6 are not equal. else is always true, and so we're going to drop that. We evaluate removing 1 from 6. Now we make the recursive call one more time. We substitute in our constant there. Five is equal to 5. And so we're going to replace it with the body, which in this case is just x. Now, we go to do this math, and we realize, wait, x is not, that's not our value. So we need to substitute in and now 7 plus 11, and we get, it's a lot of steps, but if you're struggling trying to solve some recursive problem, this is actually something that you can do to convince yourself, or at least to better understand exactly how the recursion is working. Any questions about this? All right, I will leave it on the board, so if you want to take a photo after class, you're more than welcome to do so. All right. Well then, if you have a clicker, question? Are the questions on the test going to be that long? No. Not quite that long. Originally it was, and then I was like, number one, I don't want you to spend the next hour writing, but I don't want to mark that crap either, so this is how exam writing works for me. The question's got to be a good question, but it's got to be easy to mark, because if I spend the next week marking it, I'm going to be bashing my head into a wall. So what's the nicest question I can ask while making it the easiest thing to grade? That's how your exams get written. All right. I'm trying to beat a record. There was once a time where we graded, I think it was a 135 exam, and it took us 3 hours. So let's see if we can beat that record. I think that was in a fall term too, so to be fair, I think the average was either really, really high or it was super low. It was a long time ago. All right, anyways, clickers, if you have it, get it out.
B咋可以啊 ？B 怎么不可以 ？B 怎么可以啊？为什么？因为 cos 后面要么跟 empty 一样，cos。不是啊。进入自己。11了。11了。
All right, I'm going to turn this off in about 4 seconds, so if you haven't clicked in, please do. All right. So let's see what everybody answered. Wow, that's awesome. Good job. The answer is obviously E. Yeah, you can't. Cons takes two arguments. The first argument is an item and the second argument is a list. So if you're passing it 3 arguments, you're doing it wrong. And if the second argument is not a list, you're doing it wrong. And what the hell is list of? It doesn't make any sense. That's stuff we use in the contract. That's for humans, not for rackets. So it's this one. I think that might be a record. I've never had this happen, actually, where everybody actually gives the right answer. Even when we give the right answer to you, there's always a rebel. Huh. That's fun. All right. So this is asking not about what is true about cons. This is asking what is true about the cons predicate. And if you don't remember what it does, if you have a laptop in front of you, you know, you could open Dr. Racket and type it in. All right, let's stop this. If you haven't pushed it, do so now. All right. Lots of division on this one. So the answer, by the way, is B. So first off, it's not C, D, or E, because cons question mark is a predicate, and we know predicates are supposed to produce Boolean values. A list is not a Boolean value. A list is a list. So it can only be A or B, and it's not A. So cons produces true if the provided list is non-empty. All right, we've got one more about simple recursion. Now, when we're referring to base case here, we're referring more globally to when do we stop recursing. All right, so lots of division again on this one. The answer is actually D. So if you have a recursive function, you have to have a base case. Because if you don't have a base case, you recurse forever, and that would be generally a bad thing. So it's not C, and everybody got that, so good job there. Now, the rest of it's kind of confusing because you have been taught a pattern, that template, that has exactly one base case and exactly one recursive case. So it's very easy to believe that it could be A, B, or E, but it's not for simple recursion. Simple recursion is just stating that each recursive step makes exactly one step towards a base case or stopping condition. Doesn't say about how many recursive cases there have to be. And in fact, you've already seen a function that had more than one. If I want to sum all of the even numbers or produce a list of all of the even numbers, then I would have two recursive cases. One where the current number is even and one where the current number is odd. That's two separate recursive cases, but it is still simple recursion. And I can have multiple base cases too. For example, if I am presented with a list of numbers and I want to know, is the number 5 in the list, I don't need to continue recursing if I find the number 5. I can immediately stop. So that's a base case. And an empty list is also a base case. Still simple recursion though. So simple recursion, we can actually have multiple stopping conditions and we can have multiple recursive cases. It's totally possible. And you've already seen functions that do this. All right. Morning class got a freebie, so do you guys. Let's do it again. But you got 20 seconds this time. All right. 2 rebels. And we know who they are.
I wasn't a rebel, I promise.
All right. You seemed awfully excited about that. All right. Don't worry. When it's an extra or a bonus question, everybody gets the mark. So we're not going to be unfair to the rebels out there. All right, so before we get into our topics of the day, just a couple things to remind you of. Assignment 3 is due today, like in a few hours. So if you're really bored, feel free to work on it right now. As long as you're not, watching football at maximum volume, I don't really care. Assignment 4 is out and you should get started. Assignment 4 has lists with recursion. It's fairly simple recursion, but it's still got recursion on it. And assignment 5 will be coming out this week as well. I know that's not on your mindset right now, considering A3 hasn't even gotten to its deadline, but it will be coming. And then a quick reminder that if you haven't done assignment 0, please do it. Roger, do we have anyone left with A0 outstanding? Oh, yay, I can stop saying this then. Okay, well, we're not going to worry about them then. All right, so the last few classes we focused on a few topics. We focused on introducing you to lists, which are one of the absolute key elements of the Racket language and scheme and Lisp as well. And in order to discuss lists, we had to introduce recursion. We gave you data definitions for lists and lists of different things. And we showed you how to make template functions, which is that basic pattern for how do I work with a piece of data of this particular type. And that template is really, really useful because it's the guide, it's the framework for how do I write a function that operates on this particular data type. Now, will you always follow the template exactly? No. But a good majority of the functions you will write that work on that particular data type will follow that template. So it's very useful. And again, this is just information we are providing to our fellow developers and to our users so that they can understand the data types that we've created and know how to use them better. All right, so today we're going to move on to talking about lists and a little bit more useful uses of lists than just, is the number 5 in the list and what's the sum of the items in the list? That's interesting, but there's more interesting stuff that we can do with lists than basic summing and searching. So this is for anyone actually following along with the notes. This is module 8. And the first thing we want to talk about, and we don't actually talk about it too much, is sorting. Now, sorting is actually a big discussion in computer science. We'll do some sorting in this class, You will do lots more sorting in CS136, and then you will prove the hell out of sorting in CS240. Yes, as you move on in CS, you're going to be taking a piece of code and writing a formal mathematical proof out of it. Yay, right? I see a lot of shaking heads. It's fun, I promise. And sorting is actually one of those things that we actually like to write a lot of proofs about. So, what is sorting? I have a bunch of students in this room, and I want to order you according to your grade in this course. So we're going to put all the people, what I want to do is I want to put all the people who have a grade of 0, we'll put you all the way over here, and then I want to sort you in increasing order so the people who have a 100 are over there. I'm assuming most of you are familiar with the concept of sorting, at least in real life. We want to order our data so that we can more easily do things with it. For example, I could then print out everybody's results, and it would be in a nice order, and I could very clearly see, oh, there's 10 people who have 0 in this course. And then I could see, oh, there's 20 people with 100. Oh, so the course is too easy. We better knock the difficulty up a few notches. So sorting it actually helps us understand our data, and we can actually use a lot of really interesting algorithms on a sorted list of things. Now, how do you sort? Well, we have a list, and that's what we're going to sort. I want to take a list, and I want to sort the items in that list so that they are in a non-decreasing order. That is, we're going from the smallest to the biggest elements. And interestingly, we're going to do this just with simple recursion. Now, there's lots of different sorting algorithms, and if you've done computer science or any kind of computer programming in high school or before, you've probably heard about a few different sorting algorithms. And most of those people have heard of a sorting algorithm known as bubble sort. It's the first one they teach you in high school because it's really easy to do. It's also really slow. So let's think of sorting in a different way. If you're not familiar with bubble sort, don't worry about it. We're not going to ask you that. So I want to think of sorting as in terms of breaking it down into smaller problems. So let's suppose I have an empty list. I can sort an empty list. It's just another empty list because the list has nothing in it. What about a list? I want to sort a list that contains one item. Well, if I sort a list that contains one item, that would be me inserting an item in place into an already sorted list of no items. It's an interesting way to think about it. What if I want to sort a list of 2 items? Well, that is me inserting an item into an already sorted list of 1 items. And sorting a list of 3 items, that's inserting an item into a sorted list of 2 items. We're thinking about sorting in terms of I want to combine the nth item with the solution for the n-1 items. This particular sorting that we've just done here is called insertion sort. We are going to take an item and we are going to insert it into the correct place in an already sorted list. And we're going to do it with simple recursion. And it's actually really, really simple to do. And one of the really cool things I've always found about Scheme and Racket is that the sorting algorithms are really short. If you were to write the equivalent function in something like Java or C or C++, it's going to take you a lot more lines of code. It's very easy to do these things in a Racket. Okay, so simple recursion. I want to insert an item into a list of already sorted items. So, taking my template, my base case I already know. If the list is empty, then the sorted list is also empty. Otherwise, I'm going to insert my current item into my list of already sorted items. How do I do that? Okay, well, let's just replace the how do I combine result n with the results for n-1 with insert. So if it's empty, I produce empty. Otherwise, I'm going to insert the current item, which is the first of the unsorted list, into the sorted remaining list. We haven't really done anything though, have we? Because we haven't actually described how you insert into the list. So that's the next part. How do we insert an item into a sorted list? So now we're not trying to sort a list. This sorts the list. Now we're trying to solve the subproblem of how do I combine n with the solution for n minus 1? How do I insert 5 into a list of sorted numbers? Well, now for the record, there's a trace through here. I'm not going to go through the trace. You can do that in your own review. So we're going to use still the simple recursive template for our insert function. But we've got to think about it a little more carefully. If I have an item and my list of sorted items is empty, well then my sorted list with the item added to it is just a list containing that item. So there's my base case. If the list is empty, then I produce a list containing just that item. And it's sorted because it only has one thing in it. Okay. Now, what about our other cases? Well, there's more cases to consider. What if, since we are sorting in a non-decreasing order, what if the item I want to insert is smaller than the first item of the sorted list? Well, then that would mean that the item I'm trying to insert should be the new front of the sorted list. How do we add something to the front of a list? We use cons. Okay. What if, however, the item I'm trying to insert is bigger than the first item of the list? Well, then I want to keep the current item at the front of the list, the sorted list, and I want to insert my item into the sorted remaining list. In this particular case, we actually have two stopping conditions. One, where the item gets inserted to the front of the list, and the other where the list is empty. So, there's the implementation of insert. If the list is empty, we produce the list containing the number n. And if the first item of our list is greater than or equal to n, then we are going to append ourselves to the front of the list. There's no recursion here because we've inserted ourselves into the list, so we can stop. Otherwise, we're going to add the first of the list onto the solution of inserting n into the rest of the sorted list. That's our insert function. It is also recursive. And now we can put it all together, and we have insertion sort. So that's 4 lines here, plus 3 lines here. 7 lines to implement insertion sort. It's pretty good. Yeah.
Wouldn't they have to like sort through the list like a bunch of times because it like goes through it, then goes through it again?
Well, if you look at what's happening here, the first, when we called sort originally, we are, maybe the trace here will help you see this a little bit. When we first call sort, we are going to insert our item into a sorted list. But that hasn't actually been evaluated yet. And so what ends up happening is the first time we actually call insert, we're actually inserting into an empty list. And then the second time we call insert, we're inserting into a list of one item. So we're actually peeling items one by one off the old list and adding them to the new list. So we only peel them off once, insert it into the other one. Peel it off once, and insert it to the other one. Yep.
So here, sort just means from smallest to biggest?
Smallest to biggest, yes. If you wanted to sort with some other mechanism, what you would do is in the insert function, where you see we're using less than or equal to, you would replace that with whichever comparison operator you wanted to use. So if you wanted to sort things in the order of biggest to smallest, you would change that to greater than or equal to. And maybe you have some other data type, like let's say you wanted to sort strings. There is string comparison operators that you could use. So you can replace the comparison function here with whatever comparison function you want that's appropriate to the order and the type. All right. Yep.
Sorry, what was N?
Pardon?
What is
N
N?
is the number you're trying to insert. So it's the first of the unsorted list that you're trying to insert into the sorted list. So if we go back here, N is the first of the unsorted list. It's the item we want to insert into an already sorted list. All right. So that's insertion sort. And there are many other sorts. So this algorithm here, by the way, it is faster than bubble sort. But what does that even mean? What does it mean for one algorithm to be faster than another algorithm? Now, this is not something we really cover in this course, but I think it's important to know, at least for when you're reviewing your own code. It's a valuable question to ask. Every time you do a comparison, you are asking the computer to do work. Every time you make a recursive call, you are asking the computer to do work. That work is not free. And you know it's not free if we asked you to do it out on a piece of paper, because it takes friggin' ever to write all this out, right? That's not free for you, and it's not free for the computer either. So when we're looking at an algorithm, like a sorting algorithm, we're doing things like counting how many times we do comparisons and counting how many times we make recursive calls. And when we say that one algorithm is faster than another algorithm, what we are saying is that the count of the number of comparisons we do in one algorithm is less than the number of comparisons we have to do in the other. The number of comparisons we do in insertion sort is usually less comparisons than what we would do in bubble sort. Now, is insertion sort as good as you can do? No. Definitely not. There are many, many other sorting algorithms out there, and maybe you're familiar with them. If you're not, you can go on YouTube, and there's these lovely folk dancers that will dance the algorithms out for you. They'll have number signs, and they wear costumes, and they dance the sorting algorithms. People on the internet get really bored and do really weird things. I'll post a link. All right. What are the sorting algorithms? There's selection sort. There is merge sort, which is a really good one. There's also quick sort, which can be very, very bad in very rare cases, but overall is usually the fastest for general sorting. Now, all of those sorting mechanisms that I just mentioned all do something called comparison sort. They're comparing one item to every other item, or some selection of other items. There are also sorting algorithms that do not do comparisons, but they are very specialized. So another one is heap sort, but there's also one called bucket sort. Bucket sort is one of my favorites, but bucket sort can only be used in very specific cases. For example, if I wanted to sort everybody in this room according to the grade you got in this course, I would make the observation that grades, according to Quest, are between 0 and 100. And I actually don't think you can get less than 32 on Quest, although maybe that's from when I was an undergrad, I don't remember. But let's pretend 0 is the lowest grade you can get, and 100 is the highest grade you can get. Okay. Here's how I could sort you then. I could make a bucket of students that got 0, and a bucket of students that get 1, and a bucket of students that get 100. And I'm going to take the list of all of you, and I look at your grade, and I put you in the bucket that corresponds to your grade. That's much faster than insertion sort. but it can only be applied under circumstances where there are a fixed number of pots to sort you into. And we have to know what those pots are in advance. So there are lots and lots and lots of sorting algorithms. We are not really going to get into a lot of them, but as you progress through CS, you will learn a lot more about them. You will learn how to actually prove the efficiency of these different sorting algorithms and how to compare them. So that's super fun, if you like math. All right. So what's interesting then about this insertion sort is all of the functions we've done with recursion so far, how we combined the n item with the results for the n-1 item was always something simple, like cons or add, boring. In this case, the combination was another recursive function. And even though that was the case, both of those functions are still with simple recursion. All right, so that's something interesting to do with lists. What else can we do? Well, by show of hands, how many of you are bored or tired of typing cons? Everybody. And you probably already know that I hate typing cons all the time because whenever you come into my office, I always have list abbreviations on. What the hell is a list abbreviation? It's a shortcut for all that consing. So you could create a list as cons 1, cons 2, cons 3, cons 4, cons 5, empty. Or you can use a list abbreviation called list. And list consumes a number of items, and it produces a list of those items. So cons consumed an item and a list that you are appending that item onto the front of. List just consumes the items and produces a list containing them. So if we have cons expression here for n expressions to create a list, it's equivalent to list expression 1, expression 2, all the way to expression n. It's faster. Now, are you allowed to use list? Read your assignment very carefully because we don't allow list abbreviations till I think assignment 5 or 6. So until then, you're stuck with cons, but it will make your life easier. Now, that's not the only abbreviation, and you've already seen some of the other abbreviations. I've already shown you them. 2nd, 3rd, 4th, 5th, all the way through 8th. Those are technically abbreviations because 2nd is the first of the rest, and 3rd is the first of the rest of the rest, and 4th is the first of the rest of the rest of the rest. Those 3rd is an abbreviation. They exist to simplify what your code looks like, to make it more readable. Your code, you should always be striving to make your code as readable and friendly as possible. You want to imagine that you are taking somebody by the hand and showing them your code. Look at my beautiful code, isn't it so readable? It's like taking your grandmother, you bring them here to the university. Look at this ugly building. Look at this other ugly building. Except you want your code to be pretty. Nobody ever said this campus was like some feat of beautiful architecture. All right. Now, there's one more way that you can abbreviate a list, and we will not go into detail exactly what it means today, but I'd like to show it to you because it's cool and because I use it. So, 3 ways you can define a list. Sorry, I suppose that's probably really small. There we go. So that is without a list abbreviation. With a list abbreviation, we can create a constant y. Oh, isn't that so much nicer? I'm too lazy for that. Isn't that what writing programs is for? How to be lazy 101? It's because there's some manual task you don't want to do. So There's one more way you can do this. Well, what that does, yeah, it's a little bit different. And we'll talk about exactly what the quota notation of a list means at a later date. But suffice to say, if I run this code, and if you want this to work, by the way, you need to set your language level to beginning student with list abbreviations, otherwise they won't work. So make sure you set your language level. I can now print X and Y and Z, and look at that, they're all the same. So that's pretty cool. But you need to be very careful with what you're doing here, because the meanings of these three things is different. Even though they all produce the same end result, how they operate is different. Cons appends an item onto a list. List takes the items and makes a list out of them. And to quote, we'll talk about another day. And by the way, most of you have already seen the quote part, because if you turn list abbreviations off, bracket actually usually represents empty as quote, bracket, bracket. That just means empty. Shorthand. All right. So very quickly then, we can actually draw. Pretty sure you guys don't want to deal with processes. There we go. So we can actually draw this out. So we've drawn out the lists before as, you know, if we have cons 1, cons 2 empty, well that's 1 appended onto 2, appended, and then the empty marker. That is equivalent to list 1, 2. Fairly straightforward. Now you might be thinking to yourself, all right, I see how this list stuff works, and you know, I'm going to go into bracket, and I don't want to use cons anymore, and that function, you know, count down or count up, where I take a natural number and I produce a list from the numbers n down to 1, I'm going to replace cons with lists, because I don't want to see cons ever again. Well, there's a little bit of a problem with that. Let's see what the problem is. So if we go over into bracket, let's write this function. Well, we can leave these behind. So I want to make a list, and it's going to be making a list of the numbers from n to 0. Well, no, we'll just do that, right? And otherwise, list n right? No, wrong. What happens when we do this? So, I make a list of 0, that makes sense. That's what I expect it to be. But what is that? That is a list inside of a list. And if I call that's a list inside of a list, inside of a list, inside of a list, inside of, wait, that's not what I wanted to do. It's because what list does is very different from what cons does. List takes a bunch of items and makes a list out of them. So if one of the arguments to list is another list, that list becomes an item in the list. It's a list inside of a list. Cons appends an item onto the front of an existing list. If you replace in your recursive list building functions cons with list, you're going to get a deeply nested list, which is not probably what you want. You need to use a cons here. Now it's still okay to have our base case as list 0. Pretty big difference, isn't there? Be very, very careful. We use cons whenever we are trying to append an item onto another list of some arbitrary size. We use list when we want to create a fixed sized list. For example, creating a constant, passing some argument into a function, and we need 5 elements in our list. It's a shorthand for a fixed size list. Keep that in mind. All right. Now what you've seen here is we just created lists of lists. And hopefully, is there anyone in here who hasn't started assignment 3 yet? Nobody wants to admit to it? All right. If you've started assignment 3, you may have noticed that our definition of a sphere is actually a list inside of a list. There's nothing fancy about this. A list can contain anything, which means that a list can actually contain other lists. And if we were to picture what that means, well, it just means that one of those boxes where the list item goes contains a list itself. And there's 2 ways that we can actually represent that. You can actually draw the list inside of the box, or you can draw an arrow pointing to the other list. Now, obviously, the first representation and the second representation there, they are equivalent to each other, but if you're trying to fit a list of 100 items into a single box, you might have a problem. We don't care which notation you use to draw a list of lists. They're both the same, but pay attention to how many items you might have to draw in the box first. All right. And by the way, you can construct a nested list, a list inside of a list with cons. And again, we did this in assignment 3 with the spheres. It's just that the item you are adding onto the list is in itself a list. And remember that in brackets, the items in a list don't have to be the same type. They can be of any type. I can have a number, a symbol, a string, a function, you can have all kinds of things. All right. So to give you an example of using lists of lists and recursion on lists of lists, there's this sample in the notes, which is actually quite nice. And what it is let's suppose you are working for a company that wants to create some payroll software. So you've got a bunch of employees, and the information you keep about the employees is only how much money you have to pay them. So you have a bunch of employee records. And an employee record is a list of 2 items. It is their name and how much money you pay them, so their salary. And then your payroll is a list of all of these employee records. Now once you have this payroll structure, now you can start to do interesting things with it. Like maybe you want to compute how much taxes each of your employee owes. Because maybe you were that real jerk boss that didn't actually pay taxes on behalf of your employee. Who knows? Let's just suppose we want to compute how much taxes each of our employees owe. Well, we can create a list of lists for that as well. And it's now our tax records are your name and how much money you owe. And we create our tax owed structure is going to be a list of all of these tax records. So these are just lists of lists. And there's a representation there on the slide if you care to see it. Right. So we've created this list of lists, but if I tried to write that in a contract, it would be a real pain in the ass. Because it's like, oh, I gotta do like cons nat, or cons string, cons nat, or maybe I just do list string nat. It's gonna look ugly. It's not going to look readable because our functions aren't going to be describing what exactly is the format or meaning of the data that's being consumed. So we create our data definitions. So we have one here for a payroll. So we're saying a payroll list is either empty or we are adding an employee record, which is a 2-element list of a string and a number onto our payroll list. So we have a recursive definition for payroll, and similarly for our taxes owed, it is either empty or a 2-element list cons onto our taxes owed. All right. Now some of you might have been tempted to use list of X, instead of specifying what the items of the element list are, you should always try to be as precise as possible in a data definition. Remember that the data definition and the template function are really your only opportunities to share with your fellow coders and your users exactly the type and meaning of the data that is consumed by functions. So it's really important that you're precise so that they can understand and use them correctly. All right. So now we can actually create the payroll template. So if our payroll is empty, we have no employees, and we'll do something. Otherwise, if we have a non-empty list of employees, then we are going to do something with the current employee and combine that result with the results we get from doing something to the remaining employees. Fairly standard. This isn't very descriptive, let's be honest. Because it's just saying, okay, we do something with the first employee record and we do something with the rest of them. But an employee record, those elements of that payroll list, those are lists themselves. And we may do something very specific to them. So can we do better? And we could do this instead. Well, instead of just doing something with the employee record as a whole, we could indicate we're going to do something with the first element of the employee record, and then we're going to do something with the second item in the employee record, and we're going to combine that in some way with the results from the rest of the payroll. But now we've got first of first, and I've got first of the rest of the first, and if I start nesting these pretty deep with more complicated list structures, then what I'm going to end up with is something that effectively looks like me calling car and cadadar again. It's ugly. It's hideous. It's not meaningful or descriptive. If I'm somebody coming in to try to use this template, I'm going to be like, what the hell is this? What am I supposed to do with this? We can do better. So, what I would do for this particular one is I'm actually going to create a data definition for the employee record. So there is my definition for an employee record. It's very simple because it's a 2-element list. And then I'm going to create a template for my employee record. And I'm going to do something with the first and something with the second. Now you will note in my template for my employee record here that I didn't do first and rest. It's because I have a 2-element list. And if I'm going to do something to the name of the employee, and I want to do something to the salary of the employee. Well, if I do rest, then I have the salary in a list. I just want the value that is the second element of the list. And so I can either use the first of the rest, or I could use the second to get that out. So now that I have this template, I can rewrite our payroll template as the following. Note that I'm using else here instead of cons, because if the list is not empty, or if the list is empty, it's empty, and if it's not empty, well, the list is either empty or not empty, so why use cons? You should never call a predicate if there's no need to do so. So what else is there for? So otherwise, I'm going to do something with the employee record and combine it somehow with a recursive call for doing something with the rest. There. And this is fairly descriptive. And what I like about this particular solution to the problem is that the template I create for the employee record could be used to create many different employee functions. So it's not only used in the payroll record template, but it could also be used elsewhere. All right. Now what they decided to do in the slides at first is they simplified it by creating functions that dealt with the employee's name and another helping function to deal with the employee's salary. And then they replaced first of first and first of rest of first with name and amount. I still think this is too wordy, and I think it would be much simpler if we just had one template for dealing with the employee record. But they are both very descriptive, and they are both fine. I just prefer the one I do. All right. So now let's actually use this payroll template and create something. And the thing I want to create is I want to write a function that consumes a payroll and produces taxes owed. So I want to compute how much taxes are owed by each of my employees and make a list so they can look it up. All right. Now we don't have the taxes owed function in this module, but we did it before when we talked about cons. So we're going to take it for granted that taxes owed has already, or compute taxes, has already been calculated. And now we need to write the recursive function to produce that taxes owed list. So if I have no employees, then I'm going to produce empty. But if I have employees, then I am going to compute the taxes owed for the current employee, and I'm going to cons the list containing their name and the taxes owed onto the results of computing the taxes owed on my remaining employees. So now that I've thought about how the solution works recursively, I can write the function quite simply. So here we're going to do if empty, then we produce empty. Otherwise, I create a list made up of my name and the amount of taxes that I owe. I take that list and I cons it onto the result of computing the taxes for everybody else. Now this is one of those things where I personally think this solution is very messy, because I'm creating this list and I'm consing it onto a recursive call, and inside this list I'm making another function call. And what I prefer to do in this particular case, and it's kind of reflected by how I wrote the template for this, is I would create a helper function that actually produces this list, because it would make it tidier. Both solutions, however, work. So for the record, this is, they actually do it in the notes. So using the template that I have, although they still use cons instead of else, they've created this function, SR to TR, that's going to produce that tax record for that employee. But look at how much tidier this looks. It's more readable. The only problem I have with this particular solution is what the hell is SR to TR? What's in SR? What's a TR? The name they gave this function here, this helper, is absolutely terrible. If I was grading these slides, I would give this person a 0 for function names. I didn't make the slide. All right. And there, by the way, if you didn't catch the template that I had, they also have the template for that in here. Although, again, you see them using cons here. There's no reason to use cons here, because if the list is not empty, well, you're going to go there anyways. So else is fine, and actually would reduce the number of steps that we have. All right. So we've seen now a few times, both in your assignment and in this little example here, that we have flat lists. That is a list containing no other lists. So it's just flat. And we've also seen lists of lists. And you can generalize this. There's no restriction to how many layers deep those lists go. And to generalize this, instead of sitting there and saying, I have a list of list of list of list of list, no, we say, I have a nested list, which means that I have some list that contains lists of arbitrary depth inside of them. And each element of that list may have a list of a different depth. There's no restriction there. So these are called nested lists. And if you want to get some practice with nested lists and recursion, The most famous function that you can write is called flatten. And what flatten does is it takes a nested list and produces a flat list. So if I have a nested list of numbers, then my flat list would just contain the numbers. So that's a very famous function you can try to write if you want some practice. All right. Now, our data is starting to take shape here. So we started with basic things like natural numbers and symbols and booleans, and then we introduced strings, which is a bunch of chars, and lists, which are a compound data type made up of other things. And as you start to create these compound data types, not only does it start to take shape, but we start to attach meaning to the uses of those compound data types. And you might call them patterns, but we actually have another formal name for this, and it's called an abstract data type, or ADT. And ADTs are something that is one of those topics that's studied in computer science from today until the end of time. You'll do it all over the place. And what an ADT is it's some data description, a data definition, if you have it, that describes or defines how data gets created, how it gets destroyed, and how it gets interacted with. So for example, if we look at a list, and a list is an ADT, it is an abstract data type. When we have a list, we know that we can add things to a list. That's what cons is for. And when we have a list, we also know that we can access the elements of the list. We can get the first of the list and the rest of the list. That's defining how we create it, and it's defining how we interact with that particular list. But a list isn't terribly exciting. There are many, many other ADTs out there. So for example, some that we will cover in the remaining term is trees. That's a very, very powerful data type. There's also graphs. And if you go out into the world, there are vectors, there are maps, there are hash tables, there are heaps, there are all different kinds of ADTs. And they are very powerful. And here's how we use them. You have some problem that you're faced with. Let's suppose you want to go out and create competition to Amazon. So you look at the problem that you have sitting in front of you. You're going to be selling a bunch of products. So you need to create some product database, something where you can store information like the product name, the product's cost, information about reviews, a description, photos, and so on and so forth. So that's what your data needs to look like per item. And you imagine that this is how people will interact with it. The most common operation that people are going to do is search, because people are going to go onto your, we'll call it Bamazon, and they're going to be like, yeah, I want to buy a vacuum. Sorry, vacuum went in my head because it's my son's favorite word right now. So you go to your Bamazon and people want to search for things. So you want to search for vacuum. You want to be able to search based on some key. Now, items will get added to Bamazon, but not that often, and very rarely will things be truly removed. Only when people try to sell a ghost in a jar will you start removing things. All right. So that's the problem we're trying to solve. What you then do is you look at all of the different ADTs that are available to you, and you ask yourself, for my particular use case, which of these ADTs has matches? Which one of them places emphasis on a fast search? Because that's what my users are going to be doing the most of. And you find an ADT, and then you take it and you use it to implement your database. Now, what's really interesting about ADTs is we can use one ADT to actually implement another ADT. They are building blocks. I can implement a tree with a list. I can implement a list with a tree. So there are these really cool, powerful building blocks for problem solving. And the first one we want to talk about, you already have an idea, is called a dictionary. Well, what's a dictionary? You know what a dictionary is. If you want to look up a word, let's say you want to look up the word spanghue, you're going to be like, okay, I'm going to go to dictionary.com, I'm going to type in my search key. And the value I'm looking for is the definition of the word spanghue. Yes, it's a word. It means to violently throw a frog from the end of a stick. I'm not sure why that's a word. I grew up in a small town with lots of frogs, and it has never occurred to me to stick a frog on an end of a stick and throw it. Maybe bored people in the 1200s or something. I don't know. What I have, though, in a dictionary is a key value pair. The search key is what I am searching for, and the value is whatever result it produces when it finds that item. So for a true dictionary, I am searching based on the word I want to know the definition of, and the value is going to be the definition. And there's lots of other places where we use dictionaries. For example, student records. That could be a dictionary. I want to be able to look up a student based on your student number and get your record. Or Amazon, you can think of it as also using the dictionary because we want to search for the name of an object and get the product record. So dictionaries are a very, very powerful ADT, and they are used in a lot of different places. So we know how to use a dictionary, but as part of an ADT, we need to define how the ADT is going to create, destroy, and interact with our data. So if we look at a dictionary, what we're actually thinking about is, well, the number one use of a dictionary is search. So I'm going to put a lot of effort into making sure that we can look up information in our dictionary very quickly. The other two operations on data that I need to be able to do are I need to be able to add items to my dictionary because people are always making new words. And I should be able to remove items from my dictionary because words like spanghue shouldn't exist and maybe we should remove them. All right. So there's our definition. And now we have to think about how do we implement this? And since there's like 2 minutes left of class, and it's, I don't know, Toonie Tuesday at KFC, let's go. So we'll talk about the implementation of dictionaries next class. Go finish your A3.